Rfi mitigation for the Ngvla, a cost-benefit analysis. Current plans for how to deal with radio frequency interference for the Ngvla fall into three categories. The first is to document and understand the RFI landscape. The second is to list out algorithms and data processing stages at which they may be employed, and to fold these ideas into designs of the end-to-end data acquisition system. The third is an analysis to determine which of these various options are most likely to have a favorable benefit to cost ratio, and to choose a subset of ideas to focus on for initial prototypes. This talk is a summary of the analyses presented in the three Ngvla memos listed here. Radio frequency interference presents itself in many ways. It usually consists of commercial signals transmitted in the same frequency range as interesting astrophysical emissions. Sources of interference may be ground-based, airborne, or space-based, and may be present for continuous stretches of time or may be very infrequent. Different types of RFI affect an interferometer in different ways. And so let's now relate the proposed Ngvla design and array layout to how RFI may affect it. The Ngvla is expected to have 263 antennas spread out across the southwest United States. 119 of them in the central cluster are in a remote area, far away from most terrestrial RFI sources. However, any RFI that is present in the vicinity will be seen by nearly all 119 of these antennas and will result in a significant fraction of the array being affected. Some of the 114 plain spiral antennas are likely to be close to small towns with a higher incidence of human-produced interference. Airborne emitters will be seen by larger clusters of antennas at the same time, and of course all antennas will see satellite emissions. The Ngvla frequency range of 1.2 to 116 GHz also covers a very wide range of commercial transmissions. Now here is a summary of the projected RFI landscape laid out in time versus frequency space. The time axis moves from very short duration signals at the nanosecond timescales to communication protocols that typically have on-off duty cycles in the microsecond to millisecond timescale, and then to the more continuous data transmission protocols. In this figure, the colored outlines indicate what fraction of the array is expected to see the RFI. Sources in blue represent intermittent and mostly local transmitters. Green represents some of the more predictable airborne emitters, which will be seen by large subsets of the array at the same time. Brown represents space-based transmissions that all antennas will see. The shading of the boxes conveys more information. White-filled boxes are sources likely to be intermittent in time, and therefore possibly amenable to mitigation techniques that work with the gaps in between the signals. Gray boxes represent transmissions that are likely to be present throughout an observation and thus require mitigation strategies closer to those used on astronomical signals themselves. The current strategy for dealing with such RFI is to simply inspect the data at roughly 1 second and 1 megahertz time and frequency resolution, and then just discard data that have been affected. Right. To illustrate the consequences of this point, here is a simplified view of the data acquisition system of an interferometer. Signals from each antenna are digitized, Fourier transformed, and channelized before being sent into a correlator. Samples at this stage span tens of nanoseconds and are at 10 kilohertz channel resolution. The correlator then performs the multiply and accumulate step and produces output visibilities at approximately microsecond and 10 kilohertz time frequency resolution. Averaging then takes the data down to archival data rates with samples at approximately 1 second and 1 megahertz resolutions. These data are then archived and then sent for offline post-processing analysis. In current operations, it is only at this post-processing stage that RFI mitigation is applied. And it usually takes the form of automated outlier detection and flagging or masking the data prior to any subsequent processing. There are several problems with this approach. At 1 second and 1 megahertz resolutions, RFI with duty cycles that are shorter than 1 second appear continuous, and we end up throwing away good data that resides in between the RFI signals. Also, at archival data resolutions, satellite RFI is partially decorrelated. The RFI is therefore present in the data, but cannot be modeled well enough to be easily separated from the sky signal. There is also usually no interaction between observation scheduling and post-processing, and how specific science requirements depend on the RFI environment. So how would we improve upon this? The first addition would be outlier detection and spectral filtering on the real-time antenna-based data streams. These could catch sparky RFI or very strong narrowband signals. It's currently unclear what one can actually do with the data at this stage, but at the very least, one can gather metadata about the incoming RFI. Next, after correlation, we can consider two broad ranges in time resolution: microseconds to less than a millisecond, and then milliseconds to seconds. The first stage is where there is the most chance of seeing gaps in between the on-off duty cycles of commercial communication protocols. In this case, a simple masking and proper propagation of weights would suffice when passing the data along to the next averaging stage. Millisecond timescales are the coarsest time resolution at which visibilities from up to few kilometer baselines remain coherent and not decorrelated, and therefore may be amenable to imaging and signal modeling and subtraction algorithms that attempt to recover the true signal from beneath the RFI. It should be noted, though, that the true efficacy of such algorithms is currently unknown, but this is basically a placeholder for such options. Finally, one could design a centralized intelligent database and observation manager that relates a priori information about RFI, such as satellite orbits, with currently observed RFI and the observation requirements of different science targets. So this diagram represents a top-level view of how one may set up the problem of Rfi mitigation for the NGVLA. The hope is that eventually all independently all-going prototyping and R&D efforts may all fold into a framework such as this. Now, we have to move forward from a high-level architecture diagram and just a collection of ideas. So the first key point to evaluate is the cost versus benefit of each solution. For example, is there even enough of a particular type of RFI that causes a data loss significant enough to justify the development and operating cost of real-time mitigation solutions? Another point is to identify a few focus areas that will fill gaps in our knowledge and enable us to make more concretely justifiable decisions. One way to start is a Fermi estimation, which is essentially a back-of-the-envelope calculation based on a series of plausible arguments chained together. The first step is to enumerate RFI characteristics for the different types of RFI in terms of its occupancy in the time-frequency antenna space. These characteristics can then be mapped to algorithms that are best suited to each type of RFI, as well as a data processing stage at which such algorithms may be most effective. The second step is to devise metrics to quantify cost and benefit. The fraction of data lost is one obvious metric, along with the translation to an effective increase in required observing time. The cost of operating complicated analysis algorithms in real time can also be estimated from information about the algorithm details and the data rates at which they must operate. Once we have this, we can answer some questions about whether or not there is a favorable benefit to cost ratio of a particular solution. Finally, we must analyze several realistic situations and see if the basic conclusions are robust or whether they change easily with differences in the RFI landscape. This is important to establish simply because the entire analysis is being done for a future and largely unknown RFI environment that we can only make educated guesses about, and we need to be sure that we commit only to ideas that are most highly likely to stand the test of time. So all put together, we get plots such as this. The x-axis is frequency, the y-axis is the fraction of data lost, and the colors represent different classes of RFI. The proposed NGVLA bands are marked along the top, along with the 50 to 70 gigahertz oxygen gap. The fraction of data loss takes into account the fraction of affected baselines, as well as a filling factor derived from the time frequency occupancy when viewed at a data resolution best matched to the duty cycle of the signal itself. These different RFI classes were picked based on their signal characteristics and the degree of prevalence across the array. The tall purple bars are the LEO satellites. The mid-level pink bars are space-based intermittent communication protocols. The shorter dark pink bars are cell 5G and so on. This example is for the situation of only post-processing flagging, and there is no real-time Rfi mitigation. So one direct way to interpret such a plot is that if we do absolutely nothing new for the NGVLA, we will have an average of a 25 to 30% data loss with greater than 80% or 90% losses in some bands. Okay. Now let's start turning on each of the 4 mitigation options that we identified in the system diagram earlier. Here's the first one, real-time pre-correlation flagging. If I flip back and forth, it becomes clear where the improvement is. It's just in the impulsive broadband RFI. Now in our estimates, such sources are only intermittent, human-related, and affecting only a small fraction of the array. Therefore, the impact of this solution looks relatively minor, although the metadata gathering aspect remains relevant. Moving on, this is when in-correlator high time resolution flagging is turned on. Again, as I flip back and forth, it is clear that this has the potential of significantly improving the observing efficiency. This looks good, but it is important to realize that this improvement depends entirely on the presence of usable gaps in between short time duration signals. As of now, we really do not know if these gaps exist. It is reasonable to assume that they exist simply because even commercial signals have to coexist with each other, and so there must be gaps that we can work with too. But before we jump ahead and start designing complex infrastructure to implement such real-time solutions, we need to verify that real-world RFI characteristics do match. Now, what's left are the continuous signals from cell 5G and satellites. Modeling and subtraction algorithms might be able to help considerably, but we should note that they are all currently only experimental, and none have yet proved to be robust enough for routine use. Also, even if they do become more robust in the near future, they may work only with a few emitters at once. The sheer number of LEO satellites visible at the same time is likely to be too much for even these approaches. So this plot looks great, but at the moment, the only honest statement is that this is unrealistic with current algorithms, and more R&D is required before one can think of relying on such approaches. Finally, how can regulation help in all this? For LEO satellites, there may be no hope of actually turning them off, but we should at least try to confine their effects only within the transmission bands and not entire NGVLA receiver bands. It is also imperative that no cell 5G towers appear within sight of the NGVLA array core. If they do, data losses in some 5G bands could compare with the LEO satellite loss fraction simply because of the number of antennas in the core that would simultaneously see it. Other types of interference are likely hard to regulate, but the key factor that most of our ideas rely on is simply the presence of usable gaps in both time and frequency. In order to easily analyze multiple situations and scenarios and assess the robustness of our conclusions, an RFI impact calculator was written. This can be downloaded offline at the address shown below. With it, one can edit RFI characteristics, turn on or off various mitigation options, and, for example, see the estimated effects of decorrelation on fractional data loss, or say, make the assumption that a cell 5G tower appears near the NGVLA core and then calculate the data loss. The plot on the right shows a translation of the data loss fraction into the estimated extra amount of observing time required to compensate in terms of target imaging sensitivity. So here's a tool that one could use if one is interested in playing with this analysis. To conclude, our estimates are that about 25 to 30% of data may be lost if we do nothing more than what we currently do for RFI handling. The mitigation option that shows the most promise at the moment is high time resolution flagging, just post-correlation. However, this is based on the assumption of gaps in signals, and we need tests to show that this is indeed the case. The design of an RFI database and related intelligent control is also worth prototyping from the point of view of operational efficiency and examples from other observatories that have had some success with this approach. Other algorithms and options should not be designed out, but should just be considered later. Finally, regulation still has a clear role to play. Now, none of these conclusions are anything new or surprising. Variants of this have been suggested for many years, but they have, for various reasons, not materialized into production systems. The exercises described today simply give one clear way of putting hard numbers into the problem as a way of justifying and quantifying trade-offs and decisions. Even these numbers are likely to change when more prototypes are built that directly probe reality, but it's a start, and we have at least identified a list of known unknowns that must be resolved before we can proceed further. That's it. Thank you for listening.